Okay, so we are at chapter 17, more on sets. I have discussed this chapter in the start of this lecture series, Introduction to Pure Mathematics. And I have also discussed this chapter in a different lecture series on the basics of group theory or like group theory for beginners. So if you want to have a very nice idea of sets, so please go through those also, and we will discuss some of the very nice properties and definitions over here in the briefly. Okay, so let's start with union and intersection. I'll give a definition. Says that we have let A and B be sets the union of A and B written like this is the set containing or you can say consisting of all the elements that lie in set A and B, or you can say in either A or B, and this or both. And we can write this symbolically as follows, that A union B is a set which has X elements where X is coming from A or X is coming from B. This is the union. Similarly, we can define the intersection of A and B written is the set consisting of all elements that lie in both A and B. Thus, symbolically, we can write the intersection as that it is a set which consists X elements where such that X is in A and X is in B. Okay. Now we can write some examples. So number 1 says that if A has elements 1, 2, 3, and B has elements 2, 4, then their union have elements 1, 2, 3, 4, and their intersection will have elements 2 only. Okay. Number 2, we say that late A is a set which contains n elements such that n is coming from the integers where n is greater than or equal to 0. And B is a set which consists n elements from n where n is coming from set and n is less than or equal to 0. Then A union B is a set which contains, which is equal to all of the integers, because 0 is there, negative integers are in B, and positive integers are in A, and they both contain 0. So union is complete set Z, and the intersection is only the element with 0. Now we have a definition which is for disjoint sets. We say that A and B are disjoint sets if they have no elements in common, that is, their intersection is phi, the empty set. Okay. Now recall from the chapter 1 that the notation that the notation A is contained in B means that A is subset of B, and in other words, we can say that every element of A lies in B, which is to say that if X is in A, then X is in B. Also, we we define a define that A is equal to B to mean that A and B have exactly the same elements. Now, other ways of expressing the equality of two sets are that we say both A is a subset of B and B is a subset of A, or we say that X is in A if and only if X is in B, and now we say that if further piece of notation, a further piece of notation is that if we write A is only contained in B to mean that A is a subset of B and A is not equal to B. It's a proper subset. So when, and this happens when A is contained in B, we say A is a proper subset of B. Okay. So let's define a proposition. (17.1). It says that let A, B, C be sets, then A intersection B union C is equals to A intersection B union A intersection C. We can write the proof. So we say that X is inside A intersection B union C if and only if X is inside A and X is inside B or C. Okay, and then we can further say that if and only if X is inside A and X is inside B, or X is inside A and X is inside C, and this we can combine by saying that X is inside A intersection B union A intersection C. So that's how we prove it. Now we can extend the definitions of union and intersection to many sets. Union and intersection to many sets. That is, if we have A1, A2 up to AN are sets, then their union and intersection are defined as that you can say A1 union A2 union AN is a set which consists X elements, X, where X is coming from all the AIs for some I. X is coming from any AI for some I. And the intersection is a set which consists X such that X is in AI for all I. So this X should be in all the sets A1 to AN. We can give this a very concise notation. So we sometimes use the more concise notation. That notation is that if you are doing a union of n sets, you can express it as I1 to n of AI. And similarly, if you're doing an intersection of n sets, you can express it as intersection I1 to n of AI. Okay. And similarly, we can extend this definition more for the infinite sets, infinite number of sets. So likewise, if we have, or I should just say here, for infinite sets, we write these as I1 to infinity of AI, and this has the similar definition for some I, and 1 to infinity of AI, which also has the similar definition for all I. Okay. And this is how we express them. Now we can talk about another property of these sets called, not the property, but an operation, you can say, known as Cartesian product. Cartesian products give a way of constructing new sets from old. Okay, so definition. We say that let A comma B be sets the Cartesian product of A and B be written as A times B is the set consisting of all elements okay, so we call them now symbols, all symbols of the form A comma B, and then we call them order pairs also, with A is in A comma B is in B, and such a symbol is called ordered pair. And you can say two ordered pairs are like A comma B and A prime B prime are deemed to be equal if and only if we call that IFF both A is A prime and B is B prime. And we can also form the Cartesian product of more than two sets in the similar way we did the union. Now let's talk about the finite sets. So we say that a set S is finite set if it has only a finite number of elements. If S has n elements, if S has n elements, we write the order of S is n. If S is not finite, then it is infinite. Now let's give another proposition about the orders of the sets. So proposition 17.2. If A and B are finite sets, then we can write that order of A union B is order of A plus order of B minus the order of A intersection B. And let's give the proof. So we say that let the order of A intersection B is K. Now say A intersection B have K elements called x1 up to xk. Now these elements and no others belong to both A and B. So we can write that A has first all of these K elements, then it has some other A1 to AL. Similarly, B has all of these and some other B1 to BL, or you can change the notation BM, where order of A is K plus L and order of B is K plus M. Then A union B has elements x1 to xk and A1 to AL, comma B1 up to BM. And all the elements are different. So you can say that A union B all the elements are different. So A union B is K plus L plus M, which is K plus L plus K plus M minus K. And you can write that is order of A plus order of B minus order of A intersection B. And that's the proof of this proposition, right? So we can give some examples. So out of, let's say we have, let's draw that using a Venn diagram. So we have total 30 elements. And we have actually two sets. Okay, this is set A, this is set A, and this is set B. And you can say 19s are doing maths, and 17s are doing music. So we can say that there are 19 here and 17 here and 10 here. But 10 are doing both. So how many are outside? Ask the question, how many are doing neither? So these are doing maths, math, music, and these are doing both. Okay, so to answer this, so we say that order of A is 19, order of B is 17, and order of A intersection B is 10. Then by proposition 17.2, order of A union B is 19 plus 17 minus 10, and those are 26. Since there are 30, so we need to find this x, right? So you can say that we have x is nothing but 30 minus 26, which is 4. So 4 are doing neither mathematics nor music. Let's extend the proposition for 3 sets. So order of A union B union C is nothing but order of A, order of B plus order of C minus order of A intersection B minus order of A intersection C minus order of B intersection C and plus order of A intersection B intersection C. Okay. And there we will end our this part of the lecture.